Hello, everybody. I'd like first of all to thank the organizers of this conference for giving me the chance to be here today. I'm Ali Ismail, a mechatronics engineer and a software engineering student at Atalım University in Ankara. I'm glad to be with you today presenting my study entitled as Different Methods Introduced for Modeling Features of 3D Neuroimages in AD Diagnosis, a systematic literature review study. It was written by me and my advisor, Professor Gonja Menekşe from Atalım University. So, why especially Alzheimer's disease is gaining this attention in the computerized medical diagnosis research domain? First of all, Alzheimer's disease is a neurodegenerative disease that causes loss of cognitive abilities. AD, Alzheimer's disease, AD, is the sixth cause of death among older people in the US. The population of people over 60 is expected to be 2 billion by 2050. It is estimated that 100 million people will be affected by AD by that time. In our study, we focused on the usage of neuroimaging for AD diagnosis, which is the most used biomarker. That's because it provides clear interpretability of the complex brain structure, it is less invasive, it is of low risk, and it is cost effective. Deep learning in AD diagnosis. The need for machine learning for AD diagnosis and especially deep learning arose from the fact that radiologists exhibit an error percentage that may be fatal for some diseases. Early diagnosis of AD, which can be more accurately done using deep learning, can help slow down the progression of AD effectively. Deep learning methods achieved the best results or the best accuracies in the literature among machine learning methods for AD diagnosis. That's because deep learning performs the feature extraction automatically within the same pipeline with the classification process, resulting in extracting the most informative features. Also, deep neural networks can learn hidden information and patterns due to their deep architecture. We narrowed down our review to only studies using convolutional neural networks. Convolutional neural networks is a deep learning model that emulates the way the visual brain cortex works. CNNs prove to be the best machine learning methods for image analysis. So now let's go through our review protocol, including our research questions, search strategy, inclusion criteria, and screening results. We conducted our study to answer the following research questions. The first question is, what are the different approaches used to model 3D information in neuroimaging data for AD classification using CNNs? Second, what are the transfer learning models, data augmentation, recent CNN models used to overcome overfitting? What are the different? The third question is, what are the different data sets and neuroimaging modalities used by the researchers in this area? For our research strategy, we conquered four databases: IEEE, Web of Science, Scopus, and PubMed data bases using the search string displayed here. We limited our review to the years 2020, 2021, and 2022 till the 6th of August. In this slide and the following one, here our inclusion exclusion criteria is mentioned. I'm not going to read it due to the time limitation. From the four databases, we retrieved 1,506 articles. After removing duplicates, we had 709 papers. Applying our inclusion-exclusion criteria, we were left with 55 papers. So now let's get into the results of our systematic review. For the first research question, different methods were used to model the 3D information of neuroimages. Conventional 3D CNNs were used. Well-known CNN models were used. 2D CNN combined with RNN and graph CNN. As for conventional 3D CNNs, different variations with different number of convolutional blocks, fully connected layers, and max pooling layers were used. There are well-known CNN models that prove to be the most efficient models for image analysis, like ResNet, AlexNet, LeanNet, Inception, VGG, and GoogleNet. ResNet is the most used one. ResNet was developed specially to alleviate the problem of vanishing gradient. DenseNets were developed, or DenseNet was developed after ResNet, which better alleviates the problem of vanishing gradient, achieving better or higher accuracies. 3D CNNs suffered from two major problems, which are caused by the very big number of parameters of 3D CNNs. These two problems are the computational complexity and overfitting, due also to the small sizes of medical data sets. So some studies they use 2D CNNs to extract features from 2D slices from the three different views of a 3D image and modeling or capturing the interview features using LSTMs. In another study, 2D slices from the three different views of a 3D image were plugged to the 2D CNN as an RGB image modeling the interview features. Graph CNNs were used as well, where they are applied to triangulated mesh representation of 3D neuroimaging. Uh, Triangulated mesh representations are of lower computational complexity, and that's because applying graph CNN to triangulated mesh representations results in a lower number of parameters. As for different overfitting solutions, transfer learning, data augmentations, and recent architectures designed especially for this purpose were used. As for transfer learning, the first method that was used is pre-trained. It's a pre-trained method where a well-known architectures like CleanNet, GoogleNet, ResNet, which is pre-trained on a generic imaging benchmark data set, was fine-tuned for an AD diagnosis dataset. The second method is domain adoption, where the method is pre-trained on a relevant dataset having subjects from a certain AD progression stage. The After the model is pre-trained on this dataset, is fine-tuned on another dataset having subjects from different AD progression stages. One-shot learning is the third method used, where the model is pre-trained on a subset of the whole dataset and then fine-tuned on the full data set. As for knowledge distillation, a bigger model's results uh, were used to guide a smaller model, and hence the knowledge of a bigger model is transferred to a smaller model, and at the same time decreasing the number of parameters, hence reducing the overfitting problem. Data augmentation also is an approach that is used for reducing the overfitting problem. The first technique is the traditional augmentation, like rotating the image, flipping the image, translation. These traditional augmentation techniques were used in the literature. The state-of-the-art technique is synthesizing the images. This technique is used especially in studies applying multimodalities using different neuroimaging modalities, like studies using MRIs uh, and PETs, where some subjects don't have images in both modalities. So, based on the relation or the correlation between the two modalities, synthesized images are generated using GAN's generative adversarial networks for those subjects having missing images. Also, other data augmentation techniques were used in the literature. As another solution, recent architectures that were designed specially for reducing overfitting were used. Separable convolution is an architecture that decomposes the convolutional process into two stages, reducing the number of parameters significantly, and so reducing the overfitting problem. Is an example of this recent architectures. Mobile and sufficient net, which are based on separable convolution, were also used in the literature. PCA, principal component analysis, which is an unsupervised method, was used as a solution for the small data sets, small medical, for the as a solution for the small medical data sets size. As for imaging modalities and platforms, databases that were used to retrieve data sets that were used in the literature. The most used imaging modalities, as it appears here in the graph, is the SMRI, structural MRI, traditionally or generally known as MRI. PET's positron emission tomography came in the second place. PET is a neuroimaging technique that captures the changes in metabolic processes and regional chemical compositions as well, which is important for capturing the change in protein levels that cause Alzheimer's disease. fMRI is different. Functional fMRI is different from the traditional MRI, that it captures the changes in functionalities in different brain regions, while SMRI technique It creates images for the brain structure. As for the databases used in the literature, ADNI came in the first place. In the second place, AIBL database came. Oasis database was the third most database used in the literature, and there are other databases that were used as well. In conclusion, to summarize our findings, 3D CNN is the most used method for modeling 3D features, where other methods that were used to overcome the big parameter problem for 3D CNN, they suffer from information loss. Reducing the overfitting problem, domain adoption and knowledge distillation are gaining the growing attention in transfer learning, where they prove to be of better results than other approaches. Synthesizing images using GANs is the state of the art. Is the state of the art for generating uh, missing images, which is very, which is a very important solution for the medical data set small size that should have further or should be investigated more as a future work. MRI is the most used imaging modality. Uh, and finally, ADNI was the most used platform in that. Here I come to the end of my presentation. If there are any questions, I'd like to hear from you. And thank you all for listening.